So now what we want to do is we want to understand different situations or different cases of simple harmonic motion. I explained to you one of a spring mass system. Okay, I explained to you one of a spring mass system. Now I will go to another case. We'll go to a case of a simple pendulum. Okay, now what is a simple pendulum? Simple pendulum is basically a point mass suspended from a light inextensible string. This is a point mass. It is suspended from a light inextensible string. Let the length of the string be equal to L. Okay. Now suppose your mass reaches here, then what happens is and you release it, then there is one force here, mg, there is a tension here. So now if I want to suppose this angle here is theta, I can resolve this into components. This angle is also theta, these two are parallel. So I can say T cos theta is equal to mg, and I can say T sin theta is what is acting in this direction. So this is the restoring force. So T sin theta is the restoring force. Now if the displacement is in this direction, the force is acting in this direction. So I can say F is equal to minus T sin theta, and this is the restoring force. So I can say this is equal to minus T sin theta. Then for small angles, suppose theta is very small. So if theta is very small, okay, let me just go a little ahead, and then we have found out here that T is equal to mg by cos theta. So from there I can say it is equal to minus mg tan theta. Now for tan theta means for small angles tan theta is equal to theta, that is tan theta tends to theta for small angles. So I can say that F is equal to mg theta. What is theta? Theta is the angular displacement. Okay, in this case it is the angular displacement. That means you see your force is directly proportional to angular displacement. Yeah, so I can say it is simple harmonic. Now what is tan theta equal to? Tan theta is equal to x by L. I can assume that this, because x is very small, I can assume that this is a right angle triangle, and I can say this is equal to x by L. So I have here mg by L into x minus, so force is proportional to x, so it is simple harmonic. When is it simple harmonic? Only when tan theta is equal to x by L. When is tan theta equal to x by L? Only for small angular displacements. So for small angular displacements, the motion of a simple pendulum is simple harmonic, and I can say that ma is equal to minus mg by L into x. If I can cancel these two, I'll have d squared x by dt squared is equal to minus g by L into x. Right? Now, so what can I say? I can say that omega squared is equal to g by L, or omega is equal to root over of g by L, or t is equal to 2 pi by omega, that is equal to 2 pi into root over of L by g. So this is the time period of a simple pendulum. Okay, so you have time period is directly proportional to root over of L and inversely proportional to 1 upon g. Okay, so this is a very important question, because you have clocks, the older generation clocks, the pendulum clocks, which are based on this, and you get, this is a very important favorite question in many exams. You've done this in your first chapter by using dimensional analysis. Now this is the traditional actual proof for this particular situation. Okay, the time period of a simple pendulum is equal to 2 pi root over of L by g. Sometimes what they do is they give a question wherein they have a pendulum which is actually a hollow thing which is filled up with, let's say, water, and you make a small hole. So initially this mass is this is full with water, so the center of the pendulum is where the mass is. So once